Back with a couple of proofs that are based on some of the principles that we looked at in the first part of the lecture. And the reason I'm concentrating on these proofs is that both of them contain some surprises. And I want to make sure you see that by using good basic proof technique, you can get through things like this, even if they aren't quite what you're used to. So, starting with this case, the first thing to be really clear about is that you cannot instantiate this premise. It's not governed by a quantifier. The main operation is a conditional, not a quantifier, and so if you instantiate it, you're committing a fallacy. So we can't begin the proof on line 2 by instantiating, but we can make an assumption. In fact, that's really the only sensible thing we can do. So assume what? Well, if nothing else is obvious, and this is another point about good basic proof technique, if nothing else is obvious, try doing an indirect proof. And so that's exactly what we'll do here. We'll start out by assuming the denial of what we want to prove with the goal of trying to get to a contradiction. So assumption for contradiction. Now, you can't instantiate 3 either. 3 is a negation. It's not a quantified formula. But once again, if you keep good proof technique in mind, you'll remember there is something you can do. You can apply quantifier negation. And when you do, you'll get something that you actually can instantiate. So from 2, by quantifier negation, we get this universally quantified formula, and now we can extract some information from it by instantiating. Instantiate to what, though? Well, you'd only instantiate to a variable, to a free variable, if you were trying to prove a universal and you knew what universal you were trying to prove. There's no obvious reason here to try to prove a universal, so instantiating to a free variable, which would cause you to have to indent and deal with the UG rule, doesn't seem like a good idea. Instantiating to an existential name isn't a good idea either. The only reason you should do that is when you're either forced to, because you're doing EI, or when there's already an existential name in the proof and you're trying to get things to match. So good proof technique here says instantiate to any name whatsoever. We'll just pick the name A because it's handy and convenient. From 3, by UI, we get 4. And if you look at 4, it's pretty clear that it must have gotten into the proof by UI, even if you're not looking at the justification. Now, line 5, another point about just what do you do when you're going through a proof. You've got the denial of a compound on line 4, so on line 5, apply an appropriate rule to extract information. In this case, the appropriate rule would be not arrow, and I'm going to do it in 2 pieces. I'm going to extract FA for not arrow, and I'll also go ahead on the next line and extract not GA. I may not be clear yet whether I need either or both, but there's no harm in extracting both pieces of information. So that once again comes from 4, once again by the rule not arrow. Now that we got these, what can we do with them? Well, by themselves we can't do anything, but here's something else about doing proofs. If you've got a premise, you're almost certainly going to have to use it. This is not a theorem by itself, and so we're going to need our premise. How can we use our premise? In this case, it's a conditional. We could use it if we could either do a modus ponens or a modus tollens. Now, there's no hope here for modus tollens. We don't have any way to get the denial of the consequent, but we do have a way to get the antecedent. Look at line 5, look at the antecedent, and you'll see that on line 7 we can get what we need. Pardon me. So that comes from 5 by EG, and then on line 8 we can use modus ponens. So far so good, but now what are we going to do with these things? Okay, this comes, by the way, from 1 and 7 by modus ponens. Well, we've got these two existentials. We could instantiate both of them, although we just end up with two different names, let's say E and E1. So probably we are only going to need to instantiate one of them, and we might want to think about which one it would make more sense to instantiate. And here you might notice something. If we instantiate line 8, we get GE, or any other existential name, but we'll stick with E. And look at 6 and 9. If they only had the same term, we'd have a contradiction, and that's exactly what we need. Except for the difference in the term, we have a contradiction. It's what I call an almost contradiction. Now, from the point of view of logic, the almost contradiction is not a contradiction at all. But from the point of view of what we can do in our proof, it reminds us of something. This A got into the proof by universal instantiation. We could have instantiated anything. It wouldn't have helped to instantiate to E, because that would just make us instantiate to E1 here. But the fact that it came by universal instantiation means we can go back to the source on line 3, and we can instantiate again, this time to E. It doesn't happen every time, but it happens often enough. When you have a universal, you may need to instantiate it more than once, sometimes to one term, sometimes to another. And that's exactly what's going on here. So with a bit of abbreviation, we can get not GE on line 10. The abbreviation is 3, universal instantiation, and then we apply the rule not arrow. This gives us our contradiction. 9 and 10 contradict. And then I'll let you finish it up, but to finish this, all we need to do is draw a scope line that covers all of our steps from 2 to 11, unindent, and then as our conclusion, write the thing that we were trying to get on line 1. The novelty of this proof, and the thing that may not have been obvious, is that we had to instantiate line 3 more than once to two different terms. That's how we got our contradiction. And the tip-off was what I called the almost contradiction between line 6 and line 10. Line 6 didn't actually need to be in the proof. If we'd left it out, the proof would have been fine. But it served a sort of purpose strategically or psychologically. It helped us recognize that we could get a full-scale contradiction out of this so-called almost contradiction. So go ahead and complete this, and then you might want to come back to it later and try it on your own. But that's the lesson of this proof. We have to instantiate more than once sometimes, and you need to be aware that that comes up. Next proof. Here we've got a principle about confinement or extracting something from confinement. Here we've got the quantifier confined to the F. We can take it outside, in this case, if we change it. This is one of these funny things about conditionals that we talked about. This proof also has some unusual things about it. Let's go ahead and work our way through it. Once again, we cannot instantiate the formula on line 1. It's not a universal. It's a conditional. You can't instantiate a conditional. You can only instantiate formulas that are governed by quantifiers, and this one isn't. Once again, there may be no obvious way to proceed except to make the assumption that the conclusion is false, an assumption for contradiction, and you really want to have that as just a standard move that you make when you're doing proofs. Using indirect proof is very often the way to go. So this is an assumption for contradiction. We've got the denial of a quantified formula, and so we should go ahead and apply quantifier negation. So far, everything is completely standard, completely routine. Now, line 4. At this point, we have a choice. We want to instantiate line 3, and we could do exactly what we did in the previous proof. We could instantiate it not to a variable, not to an existential name, but to a name. And I'd like you to try doing the proof that way on your own. But that's not what I'm going to do here. So let me stress that. I really do want you to try doing that on your own. It'll work out, and you'll see a lot of similarities with the previous proof. But I'm going to do something different here just to show you that sometimes when you peek ahead, you can see other ways to go. We know we need to use line 1, and we know that we're either going to do that by a modus ponens or a modus tollens. If we got not p, we could do a modus tollens, and I think you can see that by using line 3 and instantiating to anything we like, we're going to get not p. But you might also notice something else. If I could get for all x f of x, I would be able to get p. And so that would equally well allow me to make use of my premise. So just for the sake of variety, let's do it that way. We want to find a way to use line 1. We can do that if we could get for all x f of x, and it may be obvious to you that we actually can do that. If it's not obvious, it's what I want to stress here. Why do we know that we can get for all x f x? Because we know that when we instantiate line 3, we can instantiate to anything we like, and by an application of not arrow, we'll get f of that term, if it's x or a or e or whatever the heck it is. In other words, from line 3, it pretty clearly follows that everything is an f. So if we can get a free variable into the proof, which we'll do here by instantiating to x, we'll be able to prove for all x f x. So 3 and universal instantiation gets us not fx arrow p. We can get fx from 4 by not arrow. And then we can universally generalize. On line 6, we can get for all x f of x. 5 universal generalization. Now we can get p. That's from 1 and 6 by modus ponens. And we can get a contradiction because although we can't go back and use line 4 again, your line 4 is behind a scope line, we can look at line 4 and sort of see that getting something of this form will let us get not p by using the rule not arrow. Can we get something of this form again? Sure we can. 4 got into the proof by universal instantiation from line 3. We can go back to line 3 and we can instantiate to anything we like. It doesn't matter what it is. Let's just pick, just for the sake of a name, b this time. We'll instantiate line 3 to b. The b part isn't actually doing any work except letting us instantiate. It's just the fact that when we instantiate, we have to pick some term or other. So this comes from 3 by universal instantiation. The point here is we had to instantiate the universal twice. As in the previous proof, we had to instantiate it twice. Here the issue isn't an almost contradiction, but nonetheless, it's what we had to do. So we don't have an almost contradiction. Rather, what we get on line 9 is not P itself, which gives us an outright contradiction in this case. From line 8, by not arrow, we get line 9, which contradicts line 7. There is our contradiction. Seven and 9 contradict. So we've completed the indirect proof that we began on line 2. Now, that means on line 11 we can write what we originally set out to prove. And this proof worked out to be about the same length that it would have been if we'd done things the other way, but it's an equally good way to prove the proof, to prove the result rather. So what's the lesson of this proof? Well, the first point was that we knew we needed to use line 1, and we knew that there was more than one way to do it. Either way would have worked, but we decided to pick proving the antecedent, which we were able to do because of what line 3 tells us. It follows from line 3 that FA, that FB, that F whatever you like, and therefore we can prove for all x f of x. That's the insight that we made use of on lines 4 through 6. Once we got fx, we were able to get p immediately. And then the point that came up in the previous example, we had to go back to the universal and instantiate it again to something new. And when we did that, we were able to complete the proof. As I said, I really would like you to try on your own doing it just by not trying to prove for all x f x, but simply by instantiating line 3 immediately to something other than a variable on line 4 and see how the proof works out. But the big lesson to be learned from both of these proofs is that sometimes you need to instantiate the same universal more than once to two different terms.